present and or absent of the 2080. So lactobacillus casei is a probiotic strain actually, and it is a cheese isolate. Then the more common way to deliver a probiotics bacteria using a fermented product like cheese, fermented milks, and yogurt. The research on lactic acid bacteria aims to improve the flavor of product and produce a high viability of this microorganism, and also improve the functional trial related to probiotics activity. So since my strain is a cheese acid, I'm actually focusing on the cheese bacteria. So lactic acid bacteria in the cheese usually has a variety of strains like Lactobacillus plantarum, Lactobacillus coccus, lactis, and Bifidobacterium strains. And these microorganisms can be divided into two groups, which is starter lactic acid bacteria or non-starter lactic acid bacteria. The starter lactic acid bacteria usually contribute to the acids in the product, and non-starter lactic acid bacteria contribute to the texture and the taste during the cheese ripeness. So since today I'm going to focus on Lactobacillus casei, which is a non-starter lactic acid bacteria. So what's the difference between starter lactic acid bacteria and non-starter lactic acid bacteria? Starter lactic acid bacteria, it usually uses as a starter, and the population starts to go down with the time of cheese ripening. Surprisingly, non-starter lactic acid bacteria, they start growing after that, and the population keep constant and go up. So we ask the question, so the starter lactic acid bacteria will usually use the lactose in the cheese as a carbon source, as a main carbon source for these microorganisms. So we want to know if starter lactic acid bacteria use all the lactose in the cheese, what the non-starter lactic acid will use. So the other things is that during the processing of the cheese or any other product, there's different kind of stress will apply on this microorganism. Like during the fermentation, the composition of the growth media, toxic product from lactic acid bacteria, which is the acids, and dissolve oxygen. The other things is done during the downstream process, mechanisms, stress, and oxygen stress, and cell density. That's what is cell dehydration. In the storage, acidity of carrier product, food, composition of other organisms, and the other things is the most important things is the source of nutrition. So it's well documented, as I said, that cheese is lacking lactose as a major carbon source. So nutrition stress and use availability nutrition impact of the survival and metabolism formation. Therefore, I studied the effect of nutrition deprivation in Lactobacillus casei and GCRL 163 in a stationary phase and we cultured in modified MRS with a different level of lactose with the present and absent of 2080. We used three different methods to analyze the data. We use SDS to look at the protein expression, and one-dimensional liquid chromatography mass spectrometry, and we use some HPLC GCMS to look at the end products. The other things I want to say is we use a 2080 because we think 2080 might use as a carbon source in the medium. Methodology, so I have 6 different treatments. 0% lactose, which is the starvation with the present and absent of 2080. 0.2% of lactose, which is the limiting growth condition. 1% lactose is the control. And we buffer the media to control the pH. We start with the very low initial inoculum, which is 0.5, and we grow the bacteria anaerobically and incubated at 30 degrees Celsius, and we sample them differently from 1, 2, 4, 6, 8, 15, and 30 days. We have listing some samples for the SDS pH analysis and 1 DRCMS analysis, and some other samples for bacterial viability, pH, and OD. So this is the growth curve of the bacteria. So on the left side, it shows the bacterial viability. So the green color shows the 1% lactose, which is our control. So the viability of bacteria goes up, and the age starts to go down, and same with 0.2. But in 0% lactose, the bacterial viability shows high viable compared with 1 and 2. And same observation we found with the OD. And the last graph on the down end, the graph C, shows the drop of the pH in 1% lactose, which is bacteria been using the lactose but converted to lactic acids. And this is for the SDS page analysis, the 1% lactose on the left side and 0% lactose in different days, protein expressions. So there's obvious differences in between these two treatments. There's a group of protein being downregulated. So we use one DLCMS analysis to identify as much as we could of these proteins and to know what protein is up and what other proteins been down. So from the proteomics analysis, this is the bacteria, and when the lactose is present outside, the bacteria being taking the lactose and they convert it from going to the glycolysis pathway and convert it to pyruvate, and that's how bacteria make energy and making lactates. Most of these proteins being detected in this pathway and were highly abundant. But 0% lactose, of course, when there's low lactose there, those proteins were downregulated or very low abundance. The other thing is this is a heat map generated from the data from proteomics. This shows the proteins, different pathways, and the red color means the high abundance protein, the green color low abundance protein. So what we've been using, the bacteria have been using citrate and fermented to maintain the cellular energy in the medium. And when there's no 28 present in the medium I use, the bacteria will also upregulated we call it myonocytal metabolism and to make energy. So this is the citrate. So once it is present in the media, the proteins related to convert citrate to pyruvate being in 1% lactose, they wasn't really significant, but in 0% lactose will be high abundance. Here also I'm showing the metabolic map of intermediate metabolism of our citrate GCR163, 0% lactose, not 2080. I'm not going to go in details here, but the width of the arrows, it shows the high abundance of the proteins. So the proteins who've been using citrate, as I said before, converted to oxaloacetate and pyruvate and forming formates, being highly abundant. And the other things is myeloisosterenol pathway with really high abundance, and that's how the bacteria in 0% lactose, how the bacteria using this carbon source in the media to maintain the cellular energy. And this is the end product metabolism. So I'm not going to go all these graphs. So I want to look at the I mentioned here the lactic acids being highly produced with 1% lactose compared with 0.2 because of the lactose being converted to lactic acids. And the other thing is the formic acid coming from citrates. It's also been highly detected in 0% lactose because they've been using citrates. Other end products, which is octanoic acid and carbonic acid, has been detected as an end product. So where there's two things. So they've been really high produced in, or the amount of those carbonic acid and octanoic acids being high in 0% lactose with the presence of 2080 as I mentioned. So this is 0% lactose, carbonic acid being high, and octanoic acid being really also high compared with non-2080 present in the media. So this is the 2080s structure. So bacteria we thought that can break the 2080s, making octanoic acid and carbonic acids. The other thing is I make another experiment and looking on what the media has, and that the bacteria might use it as a carbon source there. So citrate, one of the things, and acid that aren't 2080, as I said. So the bacteria, so I left the media without no citrate and I put acetates there. The bacteria, the growth occurred when there's only 2080 there, but just turn a bit up when there's not 2080. And the other things, when I supply the media with citrates, also shows high probability of this high probability of microorganisms, because it's obvious from the previous result they've been using citrates. And the SDS-based analysis here, using I run to look at the protein expression when 2080 present with citrate and not 2080 with the presence of citrates. I have finished the protein analysis for whole data of this experiment, but obviously there's group of protein being downregulated when no 2080 is present there. So as I said, citrate being used, and when 2080 and citrate is in the media, the proteins was related to taking citrate compared to pyruvate when upregulated, compared with non-citrate there, where we're really downregulated, or, low abundance. So in conclusion, the study provided basic information about GCR163 response under different carbon limiting condition. Also, the data suggests that the started GCR163 induced several pathways targeting sooner energy. And that's when they use citrate or fermented citrate pathway. Under conditions like similar to this cheese ripening, citrate acid converted to acetic acid and formic acid. And the data also suggests converting of citric acid driven to pyruvate that might yield 2 ATP, and that's how bacteria might maintain the cellular energy. The other thing is, since octonic acid and carbonic acid were detected at the end product, this suggests that this citrate has ability to weakly break in or degrade in 2080, with result in metabolism in the end product. From the physiology and proteomic and metabolism data, we have shown that this citrate can grow on 2080. And then I want to thank Dr. Richard Wilson and Associate Professors Noel and CSL, University of Tasmania, helping me analyzing the data, and also some fellow PhD student and postdoc fellow in the Food Safety Center at University of Tasmania. And also I want to thank ASM giving me this opportunity to present the work, and ASM Tasmania branch to give me the Student Travel Award. Thank you.
Right, any questions for Ali on his presentation on lactobacilli? Yes, answer.
Are you saying that between 80 is naturally present in milk?
No, actually, they added to the media to prevent bacterial decoagulation. So we thought at the beginning they might not use it, and nobody actually looked at whether 2080 can be used as a carbon and source in the media. And so that's why we conducted this experiment to look, okay, what's the other things in the medium why we use as a carbon source? So we found citrates actually being used in 2080.
Okay.
Yeah.
Any other questions? Perhaps I'll take the opportunity to ask you a question, Ali. Why is it important that we need to understand about the growth of probiotic organisms under starvation conditions?
Yeah, it's thanks for the last question. And it's really important to look on the starvation, then to look at how this microorganism can behave and to maintain the viability of this microorganism in the fermented product. On the other extent, it's really important for to provide this microorganism or probiotics as a dairy adjunct for healthy benefits. Yeah.
If there are no more questions, I'd like to thank Ali for his presentation.